All right, everybody. I was walking into work this morning and I thought up kind of a standard synthesis of probability and statistics stuff problem. So um, I'm just going to do it. And I'll probably post this for both my Math 1010 and my statistics folks. Because, hey, it's a useful thing. So, um, So I've written up kind of an example problem here. Let's just begin at the beginning. Okay, so one example crash course in probability and statistics. Okay, we've got a nail factory. Um, we know that about 3 in every 100 boxes is damaged in the packaging process. So it requires packaging by hand. That's a big cost associated. So you're nervous if that percentage gets any higher. You're a maintenance worker, and you note that 3 faulty boxes in a row have to be repacked, and this is from same machine. Okay, so you know that there's only a 3% chance of a packing fault, so you compute that 3 in a row would be 0.03 cubed, or 0.000027. Just double check that calculation. It just seems ridiculous. No. 2.7 to the times 10 to the negative fifth. Boom. So it happened 27 times in 1,000, 10,000, 100,000, 27 times out of a million. Okay, not bad. So that's really low. So you suspect the machine's faulty. Yeah, so what you're saying here is you're saying you're assuming you have to assume independence for this calculation, that each one is not affecting the other, right? And you're saying basically what you're saying here is that the only reason I got such a low probability is because they're not in fact independent. They are dependent on the fact that the machine is messed up. And so the probability is actually much higher of getting 3 in a row. That's the only explanation, right? Trouble is, to get the tech guy to even turn off the machine and look at it, if he steps on the ground, that's $1,000. Then, and that's not uncommon, repair fees for just showing up for really expensive, fancy equipment. But the other thing is you're going to have to shut down the machine and lose the production. So maybe it was a fluke, but you want to watch out for it, right? And it's worth it, right? It's financially worth it to spend an hour or so, or several hours even, figuring out if this is actually working or not. It wouldn't be a waste. So we have enough evidence that it's worth formulating and testing a hypothesis. So H naught, my null hypothesis, is always that nothing special is happening, so the machine's fine. My alternative is the machine is not okay. In other words, my sampled proportion of broken boxes will be higher than the standard accepted proportion. Okay, so just a little explanation there. Since it would be over $1,000 if we didn't have to, if we didn't have to start maintenance, we should go ahead and explore. So what do we have here? Whoops. Yeah, there we go. So yeah, what do we have here? So what do? You take a systematic sample every 5th box until you have 400 of them, and 28 of them are defective. So let's check. We've got 10 successes and 10 failures because we've got 28 failures, or we won in this case. Really, winning is having a broken box. And all the rest are successes. So if we're making 400 in a couple hours, then this is definitely bigger than the population of boxes that get packed. Okay. Probability, assuming that the null hypothesis is true, probability that it happens, probability it doesn't happen, divide by sample size, square root. That gets us a normal model with these values. And I pop up in the normal calculator over here. And so So looks like I've got it plugged in already. Thank you, past Russell. 0.03. Okay. And I want to know the percent above 0.07. And I calculate and I get a 0. That's because this guy only reports 4 decimal places. That's lame. Let's look at our percentile calculator. It's a little more hardcore. So I would need a mean of 0.03, standard deviation of 0.00825. Okay. And so I know that the other calculator can't do more than 4 decimal places. And look, I'm looking at the lower p. So instead of the small probability above, I'm looking at the big probability below. So start with 5 nines, because I know the other one only goes 4 decimal places. So it has to be more than 4 decimal places. Okay, that's a percentile of, or I'm sorry, that corresponds to 6.5%. Okay, so add another 9. Okay. Okay. So it's somewhere in between 5 and 6 decimal places. Let's put a 5 there, see what happens. 5's less than 9. 6, 6. Okay, let's put a 7 there. Is it updating every time? Okay. Okay. Maybe I did away with too many 9s. Okay, 6.9%, almost 7% above. That's 99.9999% of the time it's going to be less than that failure rate, right? So only 0.000001 of the proportion of basically 1 in 1,000 million, or yeah, 1,000 million. Yeah, 1 in a million. It's a 1 in a million chance. What do you know? Yeah, so very unlikely. Go ahead and call the technician, buddy. You've done your due diligence. It's time to let somebody else make some money. All right, guys. Yeah, so just kind of a standard run through there. Let's see, cancel. Yeah, so we started out with an AND rule probability. Multiplying is AND. We investigated an independence assumption that we felt was not valid after all, which in this case meant that a machine was bad, right? The trials were not independent because they were coming out of a faulty machine. From there, we formulated a hypothesis, and we tested it using a p-value. Our p-value was much less than 5%. So we called it good. We said, yes, replace the machine. So let's just ask one more question here. How much higher than 0.03% would it have to be for us to have made, at the 5% level, for us to have made the decision? The cutoff for that is only 4.3%, 4.4%. Yeah, so well beyond that at 7%. And there we go. Hope that was helpful. Nice, quick little overview thingy. All right, folks, I'll post this everywhere, and I'll see you guys in class when I see you.